Hey, welcome. We're about to dive into a crash course on the design of microsystems. We're going to explore the tiny, almost invisible technology that has a massive, and I mean massive, impact on our daily lives. So let's get right into it.
Okay, so to get us started, let me just ask you a question. Think about your day so far. What invisible technology, something smaller than a human hair, did you rely on to get here? To watch this? To just, exist in the modern world? The answer, and this is no exaggeration, is literally all around you.
If you drove today, well, you were basically surrounded by it. We're talking dozens of microscopic sensors managing everything from making sure your airbags deploy to your car's stability control, engine performance, even your tire pressure. Oh, and it's absolutely in that phone that's probably in your pocket right now. These tiny systems are what tell your screen to rotate, they're what count your steps, and they're what help your camera get those nice, stable shots. And here's one that might surprise you. It's even in your printer, firing microscopic droplets of ink with just incredible precision. This hidden world, well, that's the world of microsystems. So let's pull back the curtain and officially welcome you to the micro world. The technology we're talking about has a name. It's called MEMS. So what does that stand for? MEMS stands for Micro-Electro-Mechanical Systems. Yeah, it's a bit of a mouthful, I know, but it actually describes them perfectly. They're tiny, micro-fabricated machines that have electrical parts and moving mechanical parts, all working together as one system, usually built on a slice of silicon, just like a computer chip. Now, this right here, this is probably the best way to understand it. If you think of a regular computer chip, an integrated circuit, as the brain that does all the processing and thinking, then MEMS are the senses and the muscles. They're the eyes, the ears, and the hands that let our gadgets actually see, feel, and interact with the physical world around them. But here's the thing, and this is super important. You can't design these senses and muscles the same way you design a brain. Nope. It takes a completely different way of thinking. You see, designing a great MEMS device isn't just about making some clever little gadget in a lab. It's about making a real-world product. So designers are constantly balancing the vision, the why. Why are we even building this? With the strategy, the what. What's it actually going to do? And the tactics, the how. How in the world are we going to physically make this thing work? It's this holistic approach right from the very start. And this tale of two chips really drives the point home. On one side, you have standard microchips, where it's all about repeating one standard part, the transistor, billions of times. But on the other side, you have MEMS, where almost every single design is a custom job. Each device is a unique three-dimensional mechanical structure built for one very specific task. You just can't copy and paste a MEMS transistor. So why all this custom work? Well, it's because when you get this small, the fundamental rules of physics start to act, well, kind of weird. And this is where things get really, really fascinating. It all comes down to a super simple idea from geometry. As you shrink an object down, its surface area doesn't shrink nearly as fast as its volume does. Basically, the outside of the object starts to matter way more than the inside, and that one simple fact has enormous consequences. Because at the micro scale, it's the surface forces that become king. Gravity, the force that runs our entire world, down at this level, it's almost irrelevant. Things don't really fall. Instead, other forces, like static cling or the surface tension of a water droplet, they become incredibly powerful. Powerful enough to move entire structures. It's completely different physical reality. Okay, so now that we've got the mind-bending physics down, let's see what we can actually build with all this weirdness. Get ready, because we're about to do a rapid-fire tour of MEMS in action. All right, let's go back to that first question. How does your phone know when to rotate the screen? The answer is a little device called a MEMS accelerometer. Now, in a textbook, they'll show you this simple concept of a little mass on a spring. But the reality inside your phone is this incredibly complex, beautiful structure of interlocking silicon combs. As you move your phone, that central mass shifts, and it changes the tiny gap between those combs. The device then measures that change electrically, and that's how it senses motion. It's just brilliant. Okay, next up. Picture this. You're on a hike, and your smartwatch tells you you've just climbed 500 feet. How does it know that? It's using another amazing device, a MEMS pressure sensor. How it works is so clever. There's this tiny, super flexible silicone diaphragm. As you go up, the air pressure changes and it causes this little diaphragm to bend. And on its surface are these things called piezoresistors. They're special materials that literally change how much electricity flows through them when you stretch them. By measuring that change, the watch can calculate your altitude precisely. And once you know to look for them, you start seeing these pressure sensors everywhere. They're in your car's tire pressure monitors, in your washing machine to detect water levels, in your fancy coffee machine to control the steam, even in critical medical equipment like ventilators. That MEMS aren't just for sensing the world. They can also be actuators, the tiny muscles that make things happen. And the range is incredible. On one end, you have a micro gripper delicate enough to handle a single biological cell. On the other, you have millions of microscopic mirrors on a single chip, each one tilting thousands of times a second to create the giant crystal clear image you see at a movie theater. And hey, remember that printer from the beginning? That's a MEMS actuator too. Each tiny nozzle uses a material that physically flexes when you apply electricity to it, and that flexing action is what fires a perfect little droplet of ink right where it needs to go. So it's pretty clear these devices are amazing, right? But making them, well, that comes with a whole unique set of challenges, which, as it turns out, are also their biggest opportunities. And really, the challenges are what make this field so exciting. You can't just order a part from a catalog. Every solution has to be a custom innovation. These devices have to interact with the messy, unpredictable real world. It takes these huge, multidisciplinary teams of scientists and engineers to pull it off. And most importantly, the design is always driven by a specific real-world problem that needs solving. And all of this, it brings us right to the edge of the future. All these principles, the sensing, the acting, the moving of tiny fluids, are now coming together, letting us shrink an entire laboratory onto a single chip. We're talking lab-on-a-chip devices that can run complex medical tests on a single drop of blood, right there at a patient's bedside. So it really makes you wonder, right? Now that we can build these incredible microscopic machines, what impossible problem are we going to solve next?